Hi friends, in this video we'll be looking at solid state chemistry part 2. So in the previous video we saw the part 1 of it, the basics of it, and if you have not watched that video, the link I will be providing in the description box, please go check it out. And now we move to the part 2, that is from radius ratio to angle between planes. Okay, so what is radius ratio? We know that in solids, we have cations, we have anions. Solids are made up of cations and anions. Now these ions arrange themselves, and when they arrange, you can find the ratio between the radius of cation to the radius of anion. And that ratio is called as radius ratio. We term the radius of cation divided by the radius of anion. This term is called radius ratio. And depending on this radius ratio, we can determine the size of the cation that is needed in a compound. Like in the case, if your cation is too small, there are certain cases, if you can look at this first picture here, you can see that the cations here are too small. Since they're too small, the anions, they can come closer. And when they come closer, there will be anionic repulsion, and this will cause an instability in our compound. Our compound would become unstable in this case, because our cation is too small. Or it can be just that our size of the cation can be a little more bigger, that the anions are just, they are all touching each other. Just touching each other means this is a stability limit. This particular radius of the cation would give rise to the stability limit. And last, we have a very large, quite large cation, so that the anions are far away from each other, and this gives rise to stability to the compound. And now that this is stable. This would be stable. So depending upon this radius ratio values, what is the radius of the cation? Depending on the radius of the cation, the value of radius ratio varies, and that can determine whether our compound is stable, unstable, or what it is. And you can also predict the coordination number of your compound using this radius ratio concept. Now if my radius ratio, the value of the radius ratio is 0.155 to 0.225, means that my coordination number would be 3, and an example of this is B2O3. That boron oxide compounds, they have coordination number 3, and their radius ratio would fall in the range of 0.155 to 0.225. Next range is from 0.225 to 0.414. This is my second range. Now here my coordination number would be 4, and an example for that would be zinc sulfide. Zinc sulfide is an example for coordination number 4. The next range that I can have is 0.414 to 0.732. This is my next range, and this would give rise to coordination number 6, and an example for this is sodium chloride, our rock salt structure. And finally, we have greater than 0.732, and this would give rise to coordination number 8, and an example for this is our cesium chloride. So from 0.155 onwards, we can have the coordination numbers and the corresponding examples. Now, if anything less than, if the radius ratio is less than 0.155, it means that the compound is unstable. So any radius ratio is less than 0.155 means it will be corresponding to this first case of instability. So this is about radius ratio. Next is packing efficiency. We know that our whole crystal system or our solid structure is made up of arrangement of atoms in different ways. The number of atoms would be different, where they're arranged would be different. So such things would be different, and depending on all that, you can have how efficiently your solid structure is packed. How you would, like, no matter however you pack it, you'll have some amount of voids in it, some amount of empty spaces in it. So how closely you have packed your structure, how efficiently it is packed, and this is given by the packing efficiency. It talks about the percentage of space that is occupied by the constituent particles here. So if we have a structure here, our unit cell like this, and if we consider the side of the unit cell to be of length A, and this is a cubic unit cell, so all sides will be equal, side is considered to be A, and if you have any atom at any particular corner, we are having atoms, and you consider the size, radius of the atoms, or radius of the atoms are considered to be R means, then how can we express the packing efficiency and how can we express the packing fraction? The difference between packing fraction and packing efficiency is that packing fraction is a fraction and packing efficiency is obtained in percentage. Now, so to get the packing efficiency, the formula is we have the number of atoms. How many atoms are there? Number of atoms in this unit cell. Like that we studied already in part 1 video, how we can calculate the number of atoms per unit cell. So, the number of atoms into volume of the each atom, volume of atom divided by volume of the unit cell. Volume of unit cell. This is how we can calculate the packing fraction. This much is the packing fraction. We would get it in a fraction number. Into 100 if I do, it would turn to packing efficiency, which is in percentage. Now let the number of atoms be some value Z into volume of the atom. Volume of the atom means atoms are in spherical shape. So spheres have the volume 4 by 3 pi r cube. R is the radius. So it's 4 by 3 pi r cube divided by volume of the unit cell. Unit cell is a cube, so cube of side A, length A, can have a volume A cube. A cube, and into 100 means we will get the packing efficiency. This is how this formula is to be utilized for finding the packing efficiency. Now this Z value keeps varying for depending on whether it's a simple cube or a body centered or face centered. That value changes. Also in all this, like in simple cube, body centered and all, the relation, we can find the relation between A and R. The length of the unit cell and the length of the sphere can have a relation between themselves, and using this relation we can cancel off things in this particular equation. We can substitute things, cancel them, and you can get a fractional number or a percentage number. Now let's move to the case of a simple cube. Let's see what its packing fraction is for a simple cube. Now here, consider two atoms. Like, yeah, simple cube has atoms at every corner. So I'm just considering two atoms that are touching each other. And we take the radius to be r. If we consider the radius of these atoms to be r, and if you consider that whole, the length of the cube to be a, this is the length of that whole cube, that is to taken to be a, means we can find the relation between them as 2r equal to a. So instead of a, I can substitute as 2r in my previous equation for packing efficiency, and packing efficiency can be calculated as Z into. So what is Z for a simple cube? For a simple cube, it is, earlier we saw in video 1, a part 1 of solid state, that for a simple cube it is 1 by 8 into 8. So the number of atoms per unit cell for a simple cube is 1 into volume of the cube was 4 by 3 pi r cube divided by, sorry, this was volume of the atom, and volume of the cube is a cube. A, instead of a, I can substitute it as 2r. So if I substitute instead of a cube, I substitute as 2r cube. So I can just cancel off things like 4 by 3 pi r cube divided by 2 cube into r cube. So r cube will get cancelled off, other things would get cancelled off, and finally this value would come out to be 52.4. Like if I'm calculating them in percentage, means into 100 would be there. This is the packing efficiency, so it's into 100. So it comes out to be, the value comes out to be 52.4%. That is the packing efficiency of a simple cube. Now we have the example of a body-centered cube which has atoms at the corners and also at the center of body part, center of the unit cell. Now I draw a line from here to here. I'm going to find a relation between this radius r and of the atoms and the edge length a of the cubes. Now let me mention this point to be a. This point is taken as b, and I draw another one more line like this point is taken to be C, and let me consider this point to be D. Okay, these are the representations that I give. Now I can apply Pythagoras here. This BC length would be A, because that's the side of the unit cell. This AD length would be A, and DC length would also be A. So now I apply Pythagoras theorem to triangle ADC. That's a right angle triangle. So I apply Pythagoras theorem, and I can find that hypotenuse square equal to base square plus altitude square. So I can say in this triangle, AC square, which is the hypotenuse square, equal to AD square plus DC square. Then AD is A square, and DC is also A. So it's again A square plus A square, that is 2A square. Okay, this is what we have. Now I take the next triangle. I have to find the length AB. AB is the one that I have to be finding, that length AB. Then I take triangle ABC. That is the next triangle that I take. There, hypotenuse square, again applying Pythagoras theorem, AB square is BC square plus AC square. That is what I find. Now this BC square, BC is A, so BC square is A square. Then AC square I already found out here to be 2A square, so I just substitute that here, 2A square. So totally this is equal to 3A square. I get it to be 3A square, or I can say that my AB equal to, taking the square root, it becomes equal to root 3A. Okay. Now, what is this AB? This is in terms of the length of the unit cell, A, edge length. Now, also AB can be this much portion. This much portion that I have is radius R. This much portion would be the whole diameter. Diameter is 2 times radius. This is 2R. And this is again, this much is radius R. So, now AB is also equal to radius R plus 2R plus R. Now that is equal to 4R. So I can get the relation between radius and the edge length to be 4R equal to root 3A, or I can say A equal to 4R by root 3. So instead of A, I can put this in the substitution in packing fraction. And for BCC, we know that the number of atoms per unit cell is 2. It's at the corners, that is 8 into 1 by 8 plus 1 at the center. So totally it is 2. So when I calculate the packing efficiency, it can be calculated as 2 into volume would be 4 by 3 pi R cube divided by, instead of A, I can substitute this equation, 4R by root 3 the whole cube. And if I substitute these values here, this would come out to be approximately, I would get the value to be 64%. Sorry, it's 68%. I would get this value to be 68% for BCC, the packing efficiency. This is into 100. So when we do this, packing efficiency comes out to be 68%. Next, let us try for an FCC structure. And for an FCC structure also, first thing is we have to find the possible relation between A and R. That is the first step. So let me just draw this here. Now I am marking this point to be A. Let me mark this point to be B, and let me mark this point to be C. I am considering the triangle ABC. The right angle triangle ACB I am considering. Now here, applying Pythagoras theorem, I know that my hypotenuse square, that is AB square, equal to AC square plus BC square. This is the concept that I have. And we know that AC is one of the sides, so that would be equal to A. BC is another side, so that would also be equal to A. So my AB square would be equal to A square plus A square. So that is equal to 2A square. Also, another thing I can find is this AB, means this much portion would be my R. This much portion would be similar to the BCC form. This would be 2R, the diameter, and this would again be R. So this AB square, or I can write AB to be root 2A. Okay, I leave that there. Then what is the other value that I can give for AB in terms of R is, it is equal to R plus 2R plus R. This is AB. That would be equal to root 2A. That is implies now I can say that 4R is root 2A implies my A would be equal to 4R by root 2. Now in the packing efficiency equation, when I calculate the packing efficiency for an FCC, we know that the number of atoms is 4, that is corners we have 1, and then 1 by 2 into 6 atoms on the faces, that would be 3. So 1 plus 3, that's 4 is the number of atoms into 4 by 3 pi r cube divided by, instead of the volume A, I give the value 4R by root 2. So 4R by root 2, the root 2, the whole cube into 100. If I do this, I would get the value to be approximately 74%. This is how I calculate for FCC. So I got for a simple cube, I got for a BCC, and I also got for an FCC, and it is found that FCC has the highest packing efficiency, which is 74%, which means that that is the most closely packed structure, we can say, with lesser number of voids. And a simple cube is the one which is least which has a lot of void spaces between themselves. It is not that closely packed. Understood. Next, we look at the density of a unit cell. We saw the packing fraction of a unit cell. Now we're going to look at the density of a unit cell. And we know that density is given by, density of the unit cell can be given by, density is mass by volume. So it would be equal to mass of unit cell by volume of unit cell. Mass of unit cell divided by volume of unit cell. Okay. And we know that the volume of a unit cell is A cube. We have always seen that when the side is of A length, then volume would be equal to A cube. Now to talk about the mass of the unit cell, mass of the unit cell would be the number of atoms it has. Z is the number of atoms into mass of each atom. If it has n number of atoms, it would be n into the number of mass of the atom we have. Now that would be the mass of the entire unit cell. Now this can also be represented in molar mass form, that is Z into this mass M. Mass of each atom M can be represented as molar mass by Avogadro number. So if I substitute all that here in this density equation, I can find that the density of my unit cell becomes equal to, instead of mass I'm substituting as Z into M by A cube, or that can also be taken in molar mass form as Z into molar mass by A cube into Avogadro number Na. This is the equation for density. This is how we can calculate the density of a unit cell, and this usually comes for exams also. So problems are asked from this part. So directly problems are asked from this part for various examinations in numerical types. So it's very simple formula and direct application. This is that value keeps varying like depending on whether it's a simple cube, body centered or face centered. Here. Miller indices. Now, what are these Miller indices? Miller indices are a notation for the planes in the crystal lattice. In our lattice, we have different planes and we can use this Miller indices to notate. They are a representation of the planes. And how do we represent them? We give the Miller indices as H, K, L. These are the notations that we use. H, K and L can correspond to any values like 1, 0, 2, 3, like any values. They correspond to values. H, K and L are the notations and they are put in parenthesis brackets. Within brackets they are put without any commas or full stop, anything with nothing between them. So I can simply represent them as like this: H, K and L in brackets. This is how I represent, give the notation for Miller indices of any plane. Now the steps to find out the Miller index for a particular plane. Now, if you look here if you look at the plane that I've drawn here, the blue color shading, first thing is I have to assign X, Y and Z axis for this. So if I go for assigning X, Y and Z axis, so this axis is taken to be the Z axis. And what I have here, this axis is taken to be my Y axis, and the axis that I have here, this axis is taken to be my X axis. And the first step that I do is I have to write down the intercepts this plane makes with X, Y and Z axis. at what point on each axis is my plane cutting the axis. So here I assume the length, that A, length of the cube, edges of the cube to be A, which is 1 unit. I take it to be 1 unit. And if you look at this picture, you can find that along my x-axis, this is cutting. Along my x-axis, this is cutting at 1 unit here. I can see that it's cutting at 1 unit. Along the y-axis also, it's cutting at 1 unit. And along the z-axis I go, there also, it's cutting at 1 unit. Okay. So it is going for 1 unit, means it is at the end of the unit cell, at the end of the unit cell, that whole 1 unit length, it is moving. The planes are moving along the x-axis, the y-axis and the z-axis. Now that I write the intercepts first, that's the first step. The first step I have to do is write the intercepts. I write the intercepts of x, y and z axis, that is 1, 1, 1. The second step that I have to do is take their reciprocals. Whatever intercepts I get, I have to take their reciprocals. Now in this case, it is 1, 1, 1. The reciprocals would also be 1, 1, 1. And the third step is I have to make them into, we have to clear the fraction part. Clear the fraction part. If at all there is any fractions, then I have to clear the fraction part. That is the next step that I do. But here there is nothing to clear fractions. They're all whole numbers only. So 1, 1, 1. And then I can represent this final third step. What I get, that would be the H, K and L values, X, Y, Z values. And this would be the Miller index for this particular plane. We look at another example. This is another example. Here I'm having my z-axis and here I'm having my y-axis, and along this plane, this as my x-axis. Okay, now look at the intercepts. So along the x-axis, it is cutting halfway through the x-axis. It has not come to this particular end. The plane has not reached this end of the cube. It is halfway through the cube. So the x-axis intercept is only half. And if I look along the y-axis, the thing what we can find is along the y-axis, if I look along my y-axis, this has not touched the y-axis at any point. My plane is moving parallel to y-axis. So the intercept should be taken as infinity. Okay. And if I take along the z-axis, if I consider, there also my plane is moving parallel to the z-axis. It is not cutting the z-axis at any point. So that is also taken parallel to z-axis. So infinity is the intercept there also. So my first step is writing the intercepts. I write the intercepts in the first step. For x, y and z, intercepts for the x-axis is half. For y-axis it was infinity, and for z-axis it was infinity. Second step is writing their reciprocals. Now to write the reciprocal of half becomes 2. Reciprocal of 1 by infinity, infinity is 1 by infinity, and that value is 0. Again for z also, reciprocal 1 by infinity is 0. Now next thing is clearing the fractions. So I have to clear the fractions if at all there is any fractions. But in this case also I do not have any fractions. So the value it is 200 only. And that can be put in the parenthesis brackets to get the Miller index. This is the Miller index for this particular plane. Now let's look at a third example where we have a fraction. We have to clear the fraction. Such an example I take. Now here also in this case I have this is my z-axis, this is my x-axis, and along here I have my y-axis. So along the y-axis it has moved 1 unit, along the x-axis it has moved only half a unit distance, and along the z-axis it's not half, it's 3 by 4. My plane has moved 3 by 4 of the z-axis, so it is cutting at 3/4 of the z-axis. Okay. Now, my first step that I should be doing is writing the intercepts. So let us write the intercepts. Intercepts for x, y and z. X-axis it is cutting at half, y-axis is cutting at 1 and z-axis is cutting at 3 by 4. The second step is writing the reciprocals. So let us write the reciprocals. So 1 by 2 would become 2, 1 is 1 only, 3 by 4 would become 4 by 3. And the third step, now here I have a fraction 4 by 3 in the z-axis, so I have to clear the fraction. And to clear the fraction, I have to multiply this 2, 1 and 4 by 3. If I multiply everything by 3, the smallest number possible integer I'm multiplying so that I can remove the fraction. So if I multiply everything by 3, 2 into 3 would be 6. This would become 3 and 4 by 3 into 3 would become 4. So now I got numbers like HK and L6. 3 and 4 would become my Miller indices for this particular plane. Clear? Okay, so now we'll be learning about Bragg's law or Bragg's equation, and this equation, a lot of questions are asked, directly numerical type questions are asked from this particular, using this equation. So let's derive this equation. So we know that from the Miller indices we saw that the crystal system has different planes. Now I'm considering that I'm allowing a ray to be incident on this crystal. A monochromatic X-ray I'm taking and I'm allowing it to be incident on this plane means then it gets reflected from this plane. Okay, so I consider a ray 1, first ray here, and that is incident on one of the planes and it gets reflected from one plane. And this angle that it falls, the angle at which it falls, that glazing angle is taken to be theta, and this angle also would be theta. This is what I consider. Now I consider another ray 2 also, second ray, which also travels, but this ray, it does not get reflected from the first plane, it gets reflected from the second plane. It travels much inwards, it penetrates much inwards the crystal system, and it penetrates to the, it falls on the second plane, and this ray also gets reflected. After falling on the second plane, this ray gets reflected from the second plane. So, according to mathematics, I can say that this angle is also theta and this angle can also be taken as theta. This is what from mathematics we can find that. And if I mention these points as A, B, C and D, I'm just mentioning, and this AB and AD that I've drawn are just two perpendiculars that I have drawn, and we can see here that my ray 1 and ray 2 does not travel equal distance, right? This up to this B point, up to A point and B points, up to these points, the length or the path traveled by, the distance traveled by both rays are equal. After coming to point B, my ray 2 has to travel an extra length BC. It has to travel an extra distance BC. This extra distance BC it has to travel before it becomes incident on any particular plane. Also, before reflecting back also, this ray has to travel, the second ray has to travel an extra difference CD before it starts reflecting. That extra distance it has to travel. Now this extra distance that the ray 2 has to travel in comparison with my ray 1, that is called the path difference. That is the path difference. I take that to be the path difference, and this path difference should be an integral multiple of the wavelength of the light or the ray that falls. If lambda is the wavelength of the ray that is falling, means monochromatic rays having wavelength lambda, means this path difference that I have. Path difference means that is that BC distance plus CD distance, that should be equal to n lambda. This is what we have to consider. Now, n is the order. N is taken to be the order of diffraction, order. Now, I have to find the value for BC and CD. How can I find? I can use the from triangles. Consider triangle. So, I take triangle ABC. ABC is the first triangle that I consider. When I consider ABC, I can apply the equation for sine theta. So I can say that my sine theta would be opposite by hypotenuse. Opposite is BC. So sine theta is BC by my hypotenuse is AC. Now what is this AC? AC is this distance. You can see here AC is this distance. And what is that? That is the distance between these two planes, and distance between any two planes is taken to be the interplanar distance, that is represented by the letter D. That AC that I have is the distance between the two planes, and that is taken to be D. So here I can substitute that to be BC by D. So I can take that to be implies my BC would be D sine theta. Okay. Similarly, I have to find the value for CD also. Now I found the value for BC. Now I have to find the value for CD also. So I take the next triangle, the other part of it in triangle ADC. That is the next part I consider, the next triangle. Again, I apply sine theta for that also. So I apply sine theta would be equal to opposite side CD divided by the hypotenuse, that is AC. Now AC is again D, interplanar distance D. So this is CD by D. So I can say that implies my CD would be equal to D sine theta. Clear? So I got the value for, now I have got the value for CD also. Now I just have to simply substitute these values for BC and CD in that first equation that I have here. This was my first equation, so I'm going to substitute the value for BC and CD that I got. So if I substitute those values, I can find that BC plus CD. So D sine theta plus D sine theta, that is equal to N lambda from equation 1, or 2D sine theta equal to N lambda. And this is the Bragg's equation. N lambda is 2D sine theta. This is the Bragg's equation. N lambda is 2D sine theta, where D is the interplanar distance, theta is that angle or diffraction angle or Bragg's angle, and N is the order, and lambda is the wavelength of light falling. Clear? So now let's find a relation between the interplanar distance. We have the interplanar distance D and we have Miller indices H, K, L. We can find a relation between these two, interplanar distance and Miller indices. There's a relation. And this relation, this equation, it is different for different crystal systems. We have cubic crystal system, we have orthorhombic, monoclinic, triclinic, different crystal systems are there and they all have different values. We'll just look at 4 different equations. So the first one is for a cubic crystal lattice. Now for a cubic crystal lattice, the equation is given by d square equal to a square by h square plus k square plus l square. This is the equation for a cubic lattice relating d and the Miller indices h, k, l, and a is the edge length. Now let's consider a second equation for tetragonal. In case of tetragonal, how would the equation be? Here, I take the 1 by d square equal to h square plus k square by a square plus l square by c square. Now, this is the equation for a tetragonal. Now, in cubic, all sides are equal, so we have only a square by. But in tetragonal, 2 sides are equal, 1 side is not equal. That's why we have a and c, a square and c square. Now, let's move to the third one. That is, we look for an orthorhombic crystal system. And the speciality of an orthorhombic crystal system is that all the 3 sides are different. A, B and C. They're different. So now we'll see how their value is. 1 by d square can be written as h square by a square plus k square by b square plus l square by c square. We have a, b, c different. So h square by a square plus k square by b square plus l square by c square. And finally, the fourth one that we have is a hexagonal system. For this, the equation is little different. For a hexagonal system, how we have the equation is 1 by d square is given by 4 by 3 h square plus hk plus k square divided by a square plus l square by c square. This is the equation for hexagonal. These are the four different crystal systems. These are the 4 different equations we have relating the interplanar distance and the Miller indices. And out of this, the first one that we have here, the cubic crystal, This is the most used equation. Generally, we consider this equation, but specifically in some questions, they can be asked for other equations also. So just know all these equations. Clear? We also have to find the angle between two planes. We found the distance between the two planes. We calculated. One was Bragg's law was there, and then also the different relating the interplanar distance with the HKL values, Miller indices values. Now let's see how we can find the angle between the planes using this Miller indices concept. So if I have two planes having Miller indices H1, K1, L1. This is one of my plane, and my second plane is having H2, K2, L2. If these are the two angles that I have, the two planes that I have with their Miller indices, then I can write cos theta. The theta is the angle between the planes, can be written as H1, H2 plus K1, K2 plus L1, L2 divided by root of h1 square plus k1 square plus l1 square into next plane h2 square plus k2 square plus l2 square. This is how I have to write the cos theta value. The angle between the planes can be written as h1 h2 plus k1 k2 plus l1 l2 divided by root of h1 square plus k1 square plus l1 square into h2 square plus k2 square plus l2 square. This is the angle between the planes. We can solve problems later with this equation also. We also have a selection rule for this Miller indices for different types of cells. We have like our primitive cell, BCC and FCC, and they have a selection rule for which all HKL values are possible for them. And this for a primitive cell, the HKL values can be any HKL value. Like I can have 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 2. Anything is possible. Any HK values, H of H, K and L can be anything. But if I consider a BCC crystal system, my H plus K plus L, when I take the sum of those values of the Miller indices, that should be equal to an even number. H plus K plus L should be even. That is, if I take 0 plus 0, 1, 1 as the plane, 0 plus 1 would be 2. That is an allowed plane. But if I take 1, 1, 1, this is not allowed in BCC because it's not allowed in BCC because 1 plus 1 would be 3 and 3 is not even, so that is not an allowed plane for BCC. And for FCC, the condition is that H, K and L, these values should either all should be odd or all should be even. We have three values, like which means that 0, 1, 1 is not allowed for FCC. 0, 1, 1 is not allowed for FCC because it is 0 is an even number and 1 and 1 are odd numbers, so that is not allowed. It should be either 0, 0, 0 or 1, 1, 1, things like that. Either all values should be odd or all values should be even. This is the conditions for this Miller indices for primitive, BCC and FCC. Clear? Okay, so that's it for today. We saw about we started with the radius ratio, then we went on to Miller indices, then we saw about Bragg's law, and interplanar distances and an angle between the interplanar distances. Finally, we saw the condition also, the selection rule also. So thank you so much. See you again with the part 3 of solid state chemistry.